Greetings, folks. It's me again, here to talk about page 2 of the notes for section 10.6. Okay. Two examples on this page. The first example is this kind of situation where they're asking you to complete an equation, kind of like figure out what's supposed to go in for this question mark. Let's see here. So the first one, it tells you you've got the square root of a times the square root of something equals the square root of a squared, which of course the square root of a squared equals a. Okay, so we're going to kind of learn a trick here that's going to help us with the problems in example 3. So let's think about this. Since those are the same index, right? They're both square roots. I can combine these by multiplying this radicand by this radicand. So the question is what times a equals a squared? Well, a times a equals a squared. So what goes in for that question mark is a. Since a times a equals a squared. Okay? Makes sense? Here, okay, slightly different because now we are dealing with third roots. The index is 3, but they're all the same, which means that same rule applies. Multiply this radicand by this radicand to get this radicand. What times y equals y to the third? Well, y times y squared equals y to the third. And why are we trying so hard to get that to be y to the third? Well, because this index in that exponent will, in a sense, cancel each other out, leaving you with just y. So that's why. All right, last one. These are all fourth roots, so we could use that same trick. We got to think about this one because here, if we're trying to figure out what multiplies by 2z to the third to get something that's a fourth root for this and a perfect fourth root for this. Well, how do I get 2 to turn into 2 to the fourth? Well, multiply it by 2 to the third. 2 to the third times 2 is 2 to the fourth, right? What do you multiply by z to the third to get z to the fourth? Well, you just multiply by z. And remember, I know my z's and my 2's look almost identical to each other, so I can hear you all now like making fun of my handwriting. Don't forget that I always put that little like slash through my z so I can tell the difference. Okay, but anyway, the question mark here equals 2 to the third times z because 2z to the third times 2 to the third z equals 2 to the fourth z to the fourth, and the fourth root of that is exactly 2z. All right. Okay, so let's use those tricks to work on the 6 examples that follow here, okay? So here's the first 2, okay? Let's get rid of these. The first 2 examples, I'm going to go from top left across. Okay, this is not simplified because there's a radical in the denominator. What I want to do to clear that is I want to make a into a to the third, because a to the third is a perfect cube root. So what do I need to do? I need to multiply both top and bottom by the third root of a squared, because what's the third root of a times the third root of a squared? It's the third root of a to the third. Don't forget to, I had to do numerator and denominator. I got to do the same to the top as the bottom. So on the top I've got 5 times the third root of a squared. And then I just kind of clean up the things that can be cleaned up. I can't do anything to the top, but this, of course, becomes a, so my final simplified result is 5 times the third root of a squared over a. Okay? All right. This one right here, same kind of situation. I've got y to the, or the fourth root of y, I should say. So I got to make y into a perfect fourth root. What do you have to multiply by y to get y to the fourth? I'm going to multiply top and bottom by the fourth root of y to the third, because y times y to the third equals, well, there's what I have on the top, right? Down here I've got the fourth root, y to the fourth, which in the end, top cannot be simplified, but the bottom is just y. Got it? Okay. All right. I'm going to erase here. I've got 4 more to go through. Okay. Next one, I've got the square root of y to the 5th over 7. So the issue here, the reason why this is not considered to be simplified is because I have a fraction in the radicand. Let's split this one up using that rule. This is the square root of y to the 5th over the square root of 7, which is the square root of y to the 4th times the square root of y over the square root of 7, which is the square root of y to the 4th is y squared times square root of y over square root of 7. But there's still an issue. We still have a square root of 7 in the bottom, so I can still do something to this to make it simplified. I can multiply top and bottom by the square root of 7, because square root of 7 times square root of 7 is just 7. So in the end you get y squared times the square root of 7y over 7. Where did the 7y come from up top? Well, that's because these are the same radical. When I multiply them, I can multiply the radicands, put them under the same radical. Okay? Okay. Next one. Square root of 8 over 3. Okay? This one looks like something that I would have done in my geometry class back in the day. Break this up. Square root of 8 over square root of 3. There's some perfect square factors in 8. Square root of 4 times square root of 2 over square root of 3. Square root of 4 is 2. Okay, so now I've got this. Square root of 3 over square root of 3, so that I can get rid of that radical in this denominator. So in the end, up top, you've got 2 times square root of 2 times square root of 3, which is the square root of 2 times 3, which is the square root of 6. And then the square root of 3 times the square root of 3 is the square root of 9. And the square root of 9 is just 3. So, there we go. Okay. Alright, what's the next one? The next one we have 15 over the cubed root of 25s. Okay, this one was tricky for me in the guided notes because my 5s and s's look very similar. I'm going to get better at that. But what do we have to do here? We got to make we got to make this radicand be a perfect cube. Okay? Got to make that radicand be a perfect cube. So what do you multiply 25 by to get a number that's a perfect cube? Again, 41 years up here. I know it's 125. 5 times 125 is that's how we get this part to be a perfect cube. What do you multiply by s to get a perfect cube? Well, s times s squared will make this portion of it become a perfect cube. So I'm multiplying numerator and denominator by the cubed root of 5s squared, because now let's take care of the numerator here. This is going to become 15 times the cubed root of 5s squared, and down here you get the cubed root of 25 times 5 is 125, and s times s squared is s to the third. Sweet. Because now, guess what you can do? You can take the cubed root of this. You got 15 times the cubed root 5s squared over 5s. And just when you thought you were done, there's one more thing you can do. You can, 15 over 5, right, is 3. So the real final result here is 3 times the cubed root of 5s squared, all divided by s. Okay. One more. You guys want to take a break? Go ahead and take a 17-second break. Okay, welcome back from your break. Let's do this last one. This last one says 18 over the cubed root of 3y squared. Okay, so we know we're going to have to multiply numerator and denominator by something to take care of this cube root in the denominator. Okay, what do I multiply by 3 to get a number that is a perfect cube? 18. 3 times 3 times 3 is 27. So I'm going to multiply this 18 by this 3. No, wait, no. Multiply by 9. Because 9 times 3 is 27. Okay, and that's going to give me a perfect cube. What do I multiply by y squared? Just y. Okay. You got to do the same thing up here, though. And now I'm ready to go. Start simplifying this. So, in the top, you've got 18 times the cubed root of 9y. Down here, you've got the cubed root 27 times y to the third equals 18 times the cubed root 9y over cubed root of 27 is 3. Cubed root of y to the third is y. All right, almost done. 18 over 3 is just 6. And I still have this stuff. The 3 is gone because I divided it into 18. What I've got left in the denominator is y. That's it. Page 3 is coming up next.